right, so you all voted for a tie between space debris and space mining. I'm just going to choose one of them. So we are going to address today space debris. What goes up must come down or not. So this is a pressing environmental concern. It's the congestion of the orbit of Earth with debris from nearly 60 years of continuous space activity. I'm gonna play this video on
Universität Braunschweig, which actively studies satellites and space debris. There are 29,000 objects bigger than 10 centimeters, only 1,900 of which are active satellites, 700,000 bigger than 1 centimeter, and an estimated 200 million objects bigger than 1 millimeter. That's 200 million objects traveling up to 28,000 kilometers per hour relative to Earth, racing over our planet.
Yeah, so that was a good summary of the problem that we have. And I just want to make sure, did you hear the audio okay?
Yeah, we could hear it.
Great. Okay, so this problem has been accumulating over time. On the right, you can see a time series where the x-axis is the year, and then on the y-axis, we have number of objects. And what you can see is that the total number of objects, which is in brown, increases very steadily over time. And what you'll also notice is that there are discrete jumps in the number of objects in space due to specific incidents, where the incidents include explosions, an anti-satellite test, which was the largest increase in an instantaneous event. What you'll also notice is that the spacecraft and rocket bodies have been steadily increasing, but the fragmentation debris has actually been increasing at different rates, more so associated with incidents than with the rocket body and the spacecraft launch rate.
Universität.
Okay, so one can ask, what's creating all of this debris? 24% of the catalog objects are satellite, but only a third of those are actually operational. Most of them are dead satellites or satellites that are past their end of life. 11% of them are spent upper stages and mission-related components. 25% of these objects in space, which there is a variety, are generated from anti-satellite tests. Here on the upper right, I have an example of, say, a rocket body, and then an institution generated a simulation where the rocket body explodes and creates a lot of fragmentation debris. So that's what all of these little shards coming from the geometry are. A lot of them, a lot of fragmentation debris comes from solid rocket motor firings, which are generated from the oxidization of some slag particles, and they are micrometeor sized. There are some that are the result of reactor cores that are depreciating over time, and droplets of reactor coolant get sprayed into space. Another historic source is the release of thin copper wires from this radio communication experiment. And there are also oxygen and microparticles that are eroding the surfaces of space objects, some of which we care about and some of which are decommissioned and are just debris creating more debris. And so on the bottom right, you can see a picture, an artistic concept of the variety of objects in space, most of which are space debris. One can ask, who is responsible for all of this congestion? So if you look at USC, I got these numbers from the, I think, USC satellite database, and this includes numbers up through September of last year. So the total number of operating satellites is about 4,500, and the United States is the one predominantly launching these satellites. where other national participants are Russia and China, but their participation is way less than ours. And then all other nationalities consist of the remaining 1,000. Now, what is the spread across these different orbits? Well, most of our satellites are in low Earth orbit, which is defined as the space between 200 and something like, shoot, I was supposed to look this up, but didn't. But I think it's something like, I'll look it up later. Anyway, low Earth orbit is the orbit that contains, say, Hubble and the Iridium constellation in the ISS. In middle Earth orbit, there are about 139 satellites, which is around this band, this gold band. And there you'll be able to see satellites like Galileo and GPS and the GLONASS satellite constellation. And then finally, we've got the elliptical orbits and the geostationary orbits. And the geostationary orbits have things like communication satellites. And what you'll also notice is right beyond the geostationary Earth orbit is something called a graveyard orbit. Sweet, I was going to say 1,000. So Haley just put in the chat that LEO is anything below 1,000 and above 200. So the geostationary Earth orbit is right below something called a graveyard orbit, which is where satellites from geostationary orbit go to die. They typically have some reserve propellant at the end of mission so that they can use some delta V to get to this graveyard orbit. Okay, now who is responsible for this congestion over time?
After 60 years of space activities, there are around 29,000 human-made objects larger than 10 centimeters orbiting around Earth. Some operational, most dead. The vast majority of these objects drift freely in orbit, at risk of collision.
All right, so that was a visualization of the distribution of satellites that we just talked about, but in 3D. And so what you'll notice when I ask the question who, it's almost a generational question. It is certainly the fact that the people who first became responsible started in the 60s, but across these generations, we have ultimately become responsible for this congestion. You'll notice that earlier in the first slide, we were talking about the distribution of the types of objects out there. We have this steady rate of payload launches, what's green, but the payload fragmentation debris is not a linear rate. It actually looks quite jumpy and discrete at points. And what you'll also notice is that the number of unidentified objects has increased in recent years. So that's something that we'll have to pay special attention to in our generation. One can ask, what are the consequences of space debris? So there are more than 560 in-orbit fragmentation events since 1961. Of those, only a small minority were actually collisions. The majority of these fragmentation events are actually explosions of spacecraft in upper stages. And I actually thought this was interesting because I also had the misperception that these were mostly collision sourced, but actually a lot of them are from explosions of spacecraft. These explosions, which are the majority of fragmentation events, create a population of objects larger than 1 centimeter, numbering on the order of 1 million. To give you a little visualization of what kind of damage can occur from space debris, here we've got 2 images that show the radius of impact for an object that is smaller than a quarter on a spacecraft wall. This is a simulation of an object smaller than a quarter going at this very thick plate at 7 kilometers per second. And this is the kind of damage that can result. Now here's another picture of the size of the projectile is that marble, and the depth and size of the impact crater is shown here. Now you can see that it doesn't take a large object to damage something very severely, as there is a huge velocity that is associated with these fragments. And just as a reminder, these fragments are increasing over time. Okay, so what is the point of talking about this? Could this problem just go away? And the answer to that question is no. This problem is only going to get worse and worse. And there is a very famous concept called collisional cascading that was dubbed by Professor Kessler or Dr. Kessler. So it's also known as the Kessler syndrome. But here on the left, what you can see is a time series plot of different objects within different orbits. So we've got geostationary in green, the mid-Earth orbit in blue, and then low Earth orbit in red. And what you're seeing is that this curve right here, that brown curve, is that little curve up until when they made this study. And so we know for certain that the number of objects over time is represented by this curve, but then this plot conjectures what is the extrapolation of the number of objects in these different orbits going at these rates that we're going at. So if you use something like Kessler syndrome or collisional cascading, you can get this mean prediction with this level of error in the confidence of number of objects that we'll see over time. And it's not a good sign. What we're seeing is this exponential increase in the number of objects that we're going to see congest space.
A hypervelocity crash between two satellites around Earth. In 2009, Iridium-33 and Cosmos 2251 collided at speeds of 42,000 kilometers per hour, smashing the satellites to bits. The biggest of the debris from this collision is still being monitored, because understandably there is a lot of it. Smaller impacts happen much more regularly. Here is before and after shots of the Sentinel-1 satellite, after an object only 5 millimeters in size impacted one of its solar arrays, leaving a 40 centimeter impact crater. Chips and nicks.
Okay, so what I wanted you to get from this video is that the Cosmos and Iridium satellite collision, they started out as these small pockets of fragments, but the size of the fragmentation debris spreads across different volumes, different masses, and so they have different drag properties that disperse them across the orbit. So that's the kind of physics that you're seeing when we're talking about fragmentation events. Yes, although the fragmentation events start in an initial cluster, what makes them extremely damaging to everything else, a liability to everything else in that orbit, is its spread across these orbits. That spread means that it's present in more places, and that high velocity means that it's possible to collide and damage other satellites.
A hypervelocity crash.
Okay. So other smart people have thought about, what do we do about this problem? How can we avoid further congestion and collisions? So the current standing international guidelines and standards propose these different practices for sustainable use of space. What we can do is design rockets and spacecraft to minimize the amount of shedding or material that becomes detached during launch and operations. So an instantiation of this is that, for example, SpaceX, instead of having upper stages that just stay in space, now these upper stages are coming back to ground and they're becoming reusable. So that is one way of minimizing the number of objects in space. Another method is to prevent explosions by releasing stored energy or passivating spacecraft once at the end of their lives. So earlier we were talking about rockets and other propulsive systems that if you just let them degrade over time can cause explosions. Well, this is the mitigation to that problem. Earlier, we talked about the graveyard orbit. That is one way of moving defunct satellites into a space so that they're not a problem. So that's for very high orbits. For very low orbits, we think about deorbiting them by increasing their drag or using up some delta V to lower them into Earth's atmosphere. And then another way to mitigate fragmentation debris is to do collision avoidance maneuvers. So say you're in an active mission and you predict that two spacecraft are going to collide with each other. Well, if you have the option to move one of them out of the way, then you can avoid a collision. And then finally, the last method I'll talk about is
Satellite in a
active
heavily
debris
trafficked
removal.
low orbit. To capture it, then
So this is ESA's proposed mission program of debris removal. What makes it interesting is that it's active. So we're sending another satellite into space to intercept a defunct satellite or object. And then we are going to rigidly attach to that object and collectively move it out of the way or out of a certain orbit. Yeah, which is pretty neat. Mechanisms are kind of cool. This net is pretty rad. So although this is very aspirational, very kind, I haven't really seen too much commitment. I really am hoping that ESA, other than talking the talk, walks the walk. My personal opinion is that it is this diffusion of responsibility, and it's very hard to get nations to commit to this problem because it's expensive and it's everyone's problem. So who's going to fix it?